horizontal projectile throw and we had vertical projectile throw. So first, let's discuss the slightly complicated one, that is vertical projectile throw. A vertical projectile throw is when I have a ball, I am throwing it up in the air, it reaches a maximum height, and then it comes back down. This kind of a throw, we were calling it a vertical projectile throw. Now, when we talk about a vertical projectile throw, let me first tell you guys the rules, and then by using a calculation, I will show you how we can apply these rules, right? When we talk about the rules, so we have, let's say, a ball. I'm throwing the ball upwards at a speed of 10 meters per second. And I'm throwing it at an angle of 30 degrees. Now, this is my velocity is 10 meters per second and the angle is 30 degrees. Velocity is a vector quantity, meaning that both the distance and the direction and the magnitude are important. Now, when I take a look at this situation that is in front of me, my velocity is acting at an angle. It's a vector quantity, meaning that I will have to take my velocity and I will have to divide it, or I will have to take it and resolve it into a vertical component and into a horizontal component, because this is a vector quantity. Since it's a vector quantity and it's not going straight, it's not going straight up, it's not going straight left, it's not going straight right. That means that this particular velocity is at an angle, which means that whenever any vector quantity, whether it's velocity, whether it's momentum, whether it's force, any vector quantity, when it is acting at an angle, we will have to make a horizontal vector and a vertical vector whenever we have any vector quantity acting at an angle. So I can take this velocity and I can resultant velocity, or the 10 meters per second, and I can divide it into a vertical component and a horizontal. Right? Now, the rules for the two components are different. First, let me just tell you guys the rules. Then I will actually tell you guys how to solve the questions related to it. And that's when the rules are going to make more sense, right? We have our horizontal component or the horizontal vector. Now, for the horizontal vector, we have a few rules. The first rule that we have is that acceleration is 0 in the horizontal direction, in the horizontal vector. So whenever I'm solving using the horizontal vector, I don't have to worry about acceleration. There is no acceleration. Acceleration is 0, right? Which means that if I want to solve the questions related to my horizontal vector, I can simply apply the formula speed is equal to distance over time. Now, here's one formula or one rule that is different for a vertical projectile motion. In a horizontal projectile throw, if you remember, we had discussed that the initial speed is the same as the speed of the throw. At whichever speed I'm throwing the ball, the initial speed is the same. And when I revise the horizontal projectile with you, we will go over it again. Now, over here in a vertical throw, situation is slightly different. It's different in this way that the initial speed has to be calculated. We will have to calculate the initial speed, and I will teach you guys how to calculate it. We will have to calculate the initial speed ourselves. It's not given in the question. They might give it in the question, but mostly we will have to figure it out ourselves. Then we have the vertical vector. When I talk about the vertical vector, so in the vertical vector, what are the rules that we need to remember? First of all, the acceleration is plus minus 9.81 meters per second squared. Why am I saying plus minus? Because if my ball is traveling upwards, my acceleration is actually minus 9.81 meters per second squared. Why negative? Because I'm working against gravity. I've thrown my ball, but I've thrown it in the opposite direction to gravity. So my acceleration is minus 9.81. Then my ball will reach a maximum height. It will reach the maximum possible height it can, and then it comes to the ground. So as it comes back towards the ground, at this point, my acceleration will be plus 9.81 meters per second square because my ball is working or now falling towards gravity. So that's rule number one. Rule number two is that if I want the speed or the velocity at maximum height is 0. Meaning that if I take a look at my ball at the very top, my velocity is 0. At this top position, the highest possible position, the velocity of the ball is 0. Rule number 3. Again, if I want to know the initial speed, I will have to calculate it. I will have to figure it out myself, right? This is different again compared to the horizontal projectile. In the horizontal throw, if you remember, I had said the vertical vector, vertically there is no speed. That's not true for the vertical throw. In the vertical throw, for the vertical vector, there is speed and we will have to calculate. Rule number 4, that if I want to solve questions related to my vertical vector, I will have to use my kinematic formulas. Now, we will take these rules and I will show you guys how you can solve questions with it. Let's take the exact same scenario. I have a ball. I'm throwing it upwards and then it's coming down. I have just two pieces of information in front of me. All I know is that I am throwing the ball with a speed of 10 meters per second. And I'm throwing it at an angle of 30 degrees. That's all the information I have. I do not have any other information. Okay, so what are we going to do in questions like these? Best thing you guys can do is always list down the data or the information provided in the question. Let's list down. We have the horizontal vector that we have to solve for, and we have the vertical vector that we have to solve for. A lot of this information that I'm going to write down, our data, is not given in the question. We are writing it down from our rules. So from the horizontal vector, we know that horizontally acceleration is 0. So horizontally, there is no acceleration. In the vertical vector, my acceleration will be plus or minus 9.81, depending upon if my ball is going up or is it coming down. Now, horizontally, when I talk about the initial speed, right? U means initial and H means horizontal vector. I don't have it. I will have to calculate it. Same is true for my vertical component. I do not have the vertical component. I don't have the speed in the vertical direction because again, like I told you guys, you will have to calculate it. How are we going to calculate it? So we are going to calculate it by making a vector diagram. My ball is traveling at 10 meters per second. I will make a horizontal component and I will make a vertical component. Sorry guys. Right? Now, this hypotenuse or my resultant is 10 meters per second. The angle with the horizontal is 30 degrees. I can find both the horizontal and the vertical simply by using trigonometry. So if I want to find the horizontal component, I can go ahead and use my cos theta. This is my adjacent, the line on which I have my angle, that is the adjacent. The other line is the hypotenuse, the opposite. And this is my hypotenuse. So cos theta is equals to adjacent upon hypotenuse. So my adjacent is h, the horizontal velocity, and my uh, angle is 30. So I will take cos 30, I will multiply it by 10, and that will give me the value for the horizontal component or the velocity in the horizontal direction. So cos 30 multiplied by 10 gives us 8.6. So horizontally, our velocity is 8.6 meters per second. So like I said, we will have to calculate. The velocity given to us, 10 meters per second, is not the velocity in the horizontal or the vertical component. We will have to use trigonometric ratios and we will have to calculate what is the velocity in the horizontal and the vertical component. Is this making sense so far? Any confusion about what we've talked about so far? Ashwish, Abuzen, I hope all clear. No confusion about how we are getting this value.
Yeah, I understand.
All right. So I can go ahead and then use sine theta to do my calculations. Sine 30 is equal to my vertical component is b, my hypotenuse is 10. So I will simply go ahead and do sine 30 multiplied by 10. I get my velocity as 5 meters per second. So I have all this information available. What other piece of information do I have? I know that at the very top, my final velocity is 0. My final vertical velocity is 0. Right? And so this is the information that we have. Now, let's go ahead and try to calculate the time. So in the question, all we're provided is with the speed and the angle. That's it. Based on these two and the information we have managed to get from our rules, I can now do my calculations over here, right? To calculate the time, what am I going to go ahead and do? To calculate the time, I will have to use a kinematic equation, right? I cannot use a horizontal vector to get my answer because the formula for horizontal vector that we have to use is speed is equals to distance over time. But I do not have the distance. The horizontal distance is not provided, right? And I don't have the time. So I cannot use the horizontal component for any calculations so far. I will have to rely on the vertical vector to do my calculations for time. So I have acceleration, I have initial velocity, I have final velocity. I can use the first kinematic equation. V is equals to U plus AT. Final velocity is 0. Initial velocity is 5. Acceleration. Now this is important. Right now, I'm looking at the ball going upwards. If my ball is going upwards, my acceleration is negative. So I will take minus 9.81 meters per second, and then I will get my t. This will go to the other side. So 0 minus 5 is minus 5. Minus 5 is equals to minus 9.81 multiplied by time. Minus 5 divided by minus 9.81 is equals to time. So if I divide the two of them, I end up getting my answer as 0.5 seconds. Now, this time that you and I just calculated, this is the time for only half of the journey. We calculated the time to get to the top, right? We use the final velocity 0. The final velocity 0 is at the top. So the time we have calculated is from the start to the very top. Now, over here, in this question, the scenario is simple. I'm throwing the ball from the ground and my ball is landing back at the ground. So my starting position and final position is the same in terms of height. I'm starting from the ground and I am landing on the ground. So it makes sense that whatever time it took for the ball to go up, it will take the same time for the ball to come down, right? So I can multiply 0.5 by 2 and that will give me my total time of 1 second, right? Now, keep this in mind. I'm only doing this in this situation because my ball is starting from the ground and it's landing on the ground. There are questions in your exams and I will discuss those questions with you where you are starting, let's say from the ground, and you throw the ball and it lands on top of a cliff or it lands on top of a hill. So in that situation, my starting position was different and my final position is different. So in this situation, you will have to find the time twice. First, you will have to calculate the time for the ball to get to the top and then from the top to the hill. Okay. I don't have to do it over here because my starting position and finishing position in terms of the ground are same. So whatever time it took for the ball to go up, the same time it takes for the ball to come down. But, and I will show you guys a question like this, where I have a ball that's going up and then it's landing on top of a hill. So now my situation is different. I'm starting from a different position, but I'm landing at a different position. So in that case, you will have to individually calculate the time for the ball to go up and then the time for the ball to go down. And then the total time will be T1 plus T2. And this will make a bit more sense when I show you guys a question related to it, right? Now, I can calculate pretty much anything at this point. I have my time, right? So my distance, for example, if I want to calculate the horizontal distance, I can take my distance. Speed is 8.6 horizontally. I want to calculate the horizontal distance. My time is 1 second. That means my horizontal distance is going to be 8.6 meters. Similarly, I can calculate the height. To calculate the height, I need to use vertical vector. We always have to match. If I'm calculating the horizontal distance, we use the horizontal vector. If I want to calculate the vertical distance, we will use the vertical vector, right? So if I want to calculate the vertical height, I can simply go ahead and use the formula v square is equals to u square plus 2as. My final velocity at the top is 0. My initial velocity is 5 plus 2. My acceleration is minus 9.81 because right now I'm talking about the ball going up. So 5 square is 25. 0 is equals to 25 plus 2 multiplied by 9.81 multiplied by s. And I rearrange my equation. So this will become minus 25 divided by 2 into minus 9.81, and I should be able to calculate my S. So 25, negative 25 divided by 2 and divided by negative 9.81, which gives us a distance of 1.27. So the vertical height covered by the ball is 1.27. So this is how you guys are going to use the information given along with the rules of the throw to calculate your or to calculate or to find the answer to questions that they have asked. Right? Making sense? Any confusion so far? Ashwesh, Abu Zaid, I hope this is all clear. There's at so far what you've talked about, there's no confusion in this.
What's the 10 meters per second minus 1 again? That's the speed.
Yes, that is the speed. The speed at which I'm throwing the ball, that's 10 meters per second.
Then you can find the velocity because then the vertical
Yes.
and horizontal have different direction.
Yes, exactly. Exactly.
Okay.
So this 10 meters per second, I will have to solve it. I will have to open it up, right? I will have to take the horizontal and vertical vector individually, and both of them will have different values. So that I will calculate by using my sine theta and cos theta. Okay. If all is clear so far, let me actually share with you guys a question on the topic. Give me 1 second. Right. Look, this is the kind of questions you guys are actually going to be seeing in your exam, and we're going to go ahead and discuss how you're going to be solving these questions, right? The question is saying a distressed player may be launched from a boat to signal for help. A flare is launched from a stationary boat at an angle of 30 degrees to the horizontal. The flare was launched to the right from the launch position marked X on the diagram below. Complete the diagram to show the path taken by the flare before it hit the sea. So we know that the flare is traveling at 30 degrees to horizontal, right? When we are going to go ahead and talk about it, this is a vertical projectile motion. So, in a vertical projectile motion, what do we remember? In a vertical projectile throw, what is going to happen? The object is first going to go up into the air and then it is going to land down, right? So that's exactly what I will draw. I will draw that my flare is going up into the air and then it is landing on the sea. This is exactly what I'm going to draw. So what this is basically us applying our knowledge of vertical projectiles. Our vertical projectiles are when an object goes first, it goes into the air and then it lands down. So that's what we had to draw and that's what we have drawn. Now, this was
How can
just
how can you be sure if it's this horizontal projectile motion? How do you
a
know if it's not?
horizontal, yeah, okay. A horizontal projectile would not go in the air, meaning that it would simply go like this, like so. So if I, for example, you're standing on top of a boat and you kick the ball. There is a ball on the surface of the boat and you kick it. That ball will simply roll down. This is a horizontal projectile motion. So it's not going up in the air. It's not going to a maximum height. It is simply traveling forward and then rolling off the ship. It's traveling forward and going down into the sea. That's a horizontal projectile motion. And a vertical projectile motion, it's first going to go up in the air and then it's going to be landing down. So if this was a horizontal projectile motion where they said that you're standing on top of a ship and you kicked a ball and it rolled off and fell into the sea, draw a path, so you would simply make it like this is the ball, it would roll off and go into the sea. So in a horizontal projectile, if I'm standing, for example, at top of a cliff, my ball is simply going to travel like this. Same cliff, but I'm doing a vertical projectile motion. So that ball will first go up and then come down. That's the two major differences between the two throws. Does that answer your question?
Yeah, thank you.
Now, the next part is saying the maximum height of the flare above the launch position was 42 meters. Show that the flare was launched at a speed of 60 meters per second. What information do I have? They have told me that the maximum height of the flare above the launch position, this. The maximum height of the flare above the launch position, this is the launch position, is 42 meters. So in this situation, they have not provided us with the speed. They have provided us with the distance. And they have said, now you calculate and you tell us what the speed is going to be. So we have to use this distance to calculate the speed. We have to use this height, maximum height, to calculate the speed at which the flare is being launched. So we have to calculate the initial speed, right? Now, how are we going to go ahead and do this particular question, right? Now, the way we are going to go ahead and do this particular question is, again, we are going to go ahead and take a look at our, we're going to go ahead and take a look at our vectors, right? We have the horizontal vector and we have the vertical vector. What are the rules that we remember about our horizontal and vertical vector? Let's take a look at our data. So we know over here, I do not know what is the velocity. I do not know what is the speed at which I'm throwing the ball. Uh, Regardless of what information you have, making this triangle will really help you guys out. So this is my triangle. I do not know what is the speed. What is this velocity? I do not know. That's the question. I do know that the angle though is 30 degrees. Now, if I can somehow figure out the vertical component, if I can somehow figure out what is the vertical component, I can use trigonometry and find out the hypotenuse, right? I want to find out the hypotenuse, the speed at which I'm throwing the ball. If I can somehow solve the vertical component, the vertical vector, if I can find out the opposite, I can use trigonometry and get my answer. I don't have to do anything else. So I need to find this. I need to find the initial vertical velocity. What is the initial vertical velocity? That's what we have to calculate. Now, what information do I have from the question? We know that acceleration will be plus minus 9.81 meters per second square. This is information we have from our rules. The rules we have studied, the information is coming from there. Next, we know that the velocity at the very top, that's the maximum height, is 0. So our final velocity is 0 meters per second. They have told us in the question that the distance is 42 meters. We need to calculate the initial velocity. So we have acceleration, we have our initial velocity, we have final velocity, that is 0. We have the distance, that is 42 meters, and we need to calculate initial velocity. So if you take a look at your 4 kinematic formula, right? Because for the vertical vector, we have to use kinematic formula. We have v is equals to u plus at. We can't use this formula because we don't have time. We have acceleration and final velocity, but not time, right? Whenever you choose a formula, make sure at least there's only one thing missing. There should only be one piece of information missing, right? Over here, I don't have the initial velocity. That's what I have to calculate. But I also don't have the time. So I cannot use the formula. Another formula I have is S is equals to U plus V upon 2 multiplied by time. This also involves time. I do not have time. I cannot use this formula. Then I have S is equals to UT plus half AT square. Again, requires the use of time, which I do not have. The final formula is V is equals to U square plus 2AS. This is the formula I will go for. It's the only choice I have. Let's apply the formula. V square is equals to U square plus 2AS. Final velocity is 0. Initial velocity, I do not know. We have to calculate plus 2. My acceleration. My ball or my flare is going upwards. I'm looking at the first part of the journey. My flare is going upwards. My acceleration is minus 9.81. The distance or the height that the flare is traveling to is 42. So I will calculate for U square. So 2. So when I take my 2, I multiply it by 9.81 and I multiply by 42, I get my answer as 824. So 0 is equals to U square minus 824 because the acceleration is negative. So when I will multiply 42 and 2 with minus 9.81, I will get minus 824. Taking this to the other side, so 0 plus 824 is equals to U square. U square is equals to 824. I will underroot my answer. So my answer comes out as 28.7. Is so far we are all clear how we're getting to 28.7?
Yes.
Okay. Now I have not completed my question. I still have one last thing to do. This u that I have calculated, this initial velocity that I've calculated is in the vertical direction. So now I know that in the vertical direction, the velocity is 28.7. Now I can use trigonometry ratios. I can use my trigonometry to figure it out, right? How am I going to do that? I'm going to use the formula sine theta is equals to opposite upon hypotenuse. Sine 30, my opposite is 28.7. My vertical is the velocity with which I'm actually throwing the flare. So I will do velocity is equals to 28.7 divided by sine 30. And when I will do the calculations, I will end up getting my answer as velocity is equals to 57.4 meters per second. And they said in the question, show that the flare was launched at a speed of about 60 meters per second. So our answer matches their answer, right? 57.4 is the exact value. Okay, so in the past paper questions, when they ask you to show that the speed is this much, show that the force is this much, so they always give you a round value. They will say about, show it is around this much. They will never give you an exact value because, of course, they don't want to give you the full answer. So when you are solving the question, so for example, when I will do part 2 of the same question, I will take it as 57.4. Okay, I'm not going to use 60. We will take 57.4. The answer you will get is going to be the exact correct answer. Their answer is more of an approximation. They don't tell you the exact answer. They say approximately this much. Show that this is approximately this much. So we are getting our answer is about 60 meters per second. If I round it off, I will get 60. But in future calculations, I'm not going to take their answer. I'm not going to take 60. I will take my answer, 57.4. All right. All clear how we're solving the question, how we're getting our answer?
Yeah, it's clear.
Okay. Now, this was actually a pretty easy part. You will see the second part is this is the kind of questions you guys are going to be seeing quite a lot, right? They're saying the flare was visible from a maximum distance of 8 kilometers. A rescue boat was 8.2 kilometers from the boat in distress. Determine whether the flare traveled a sufficient distance to be visible from the rescue boat. Right? You should assume that the flare was launched in the direction of the rescue boat. So we are launching a flare. We have a boat. We have our boat. From our boat, we're launching our flare. Now they're saying that the flare is visible from a maximum distance of 8 kilometers. We have another boat that is around 8.2 kilometers away from our boat. They are saying we have to find out that is that flare going to be seen by the boat? Is this boat going to see the flare or not? To do so, we will again have to do calculations, right? I need to know how far the flare is traveling, right? How far the flare is traveling. If the flare is traveling far enough, if it's traveling horizontally far enough, I will be able to see it from the rescue boat. If it does not travel far enough, I will not be able to see it. So I need to know to get an answer, I need to know whether the flare is so what is the horizontal distance covered by the flare. When I will launch the flare up in the air, when I will throw it up in the air, is it going to horizontally travel greater than 8 kilometers or less than 8 kilometers, right? So how are we going to do that? First thing is first, we have to calculate. We now have to calculate what? Horizontal distance. What is our goal? Our goal in solving this question is that we need the horizontal distance. Now, to calculate the horizontal distance, this is our main goal. Only when I have the horizontal distance with me, I will be able to answer their question as to whether the rescue boat will be able to see it or not. Let's see. When we talk about the horizontal distance, so what information do we have? Going back to the vector diagram we just made in the previous question. Okay. So if you remember the vector diagram, this is the vector diagram we had made. Vertically, we had gotten the speed of, I believe, 28.7. The hypotenuse we calculated by using sine 30 as 57.4. Now we can calculate the horizontal velocity as well, right? No problem. Either you can do this by using trigonometry or by using Pythagoras theorem. Up to you, right? Your choice at this particular point. We have most of the information. So I will just do quickly trigonometry. Sine cos 30 is equals to adjacent upon base. Adjacent is the horizontal velocity. So whatever my horizontal velocity is divided by hypotenuse, which is 57.4. So I will go ahead and I will do cos 30, and I'll multiply this by 57.4. That gives me y value for the horizontal component as 49.7 meters per second. So the initial velocity horizontally is 49.7 meters per second. Now, what other rules do we remember about the horizontal distance? The rules we remember about the horizontal component, right? Or the horizontal vector. The rules we remember about the horizontal vector are that there is no acceleration vertically. Horizontally. There is no acceleration horizontally. So if I want to do any calculation, I will use the formula speed is equals to distance over time. Distance I have to calculate. Speed I just found out was 49.7. I now need to go ahead and find the time. So if I want to find the time, I need to go back to the vertical component. I need to go back to my vertical vector if I want to find out the value for my time. What information do we have about the vertical vector? Well, we know this was our flare. It was being launched and it was going upwards and then it was coming downwards. So we know that the initial vertical velocity is 28.7. We calculated it just in the previous question. We know that the acceleration is going to be plus minus 9.81. We know that the velocity at the top, at the maximum height, that velocity is going to be equal to 0 meters per second. We know that the height that they gave us in the question was 42. We need to use all of this information and we have to calculate the time. Once I have the time, then I can put it back in the formula. Speed is equals to distance over time, and I can solve my question, finish it up. So now, what do you think? I need to calculate the time. What formula do you guys suggest I use over here? What do you guys think? I'll give you guys a moment. We have 4 kinematic formulas that we have discussed. Which formula do you guys think we can go ahead and apply over here, maybe in this scenario?
V equals U plus AT.
Right, we can go ahead and do that. V is equals to U plus AT. That is definitely correct. Okay, so we know that our final velocity is 0, right? We know our initial velocity is 28.7. So if I will put this in my formula, and of course my acceleration is going to be equal to my acceleration is going to be equal to minus 9.81. So you're completely correct. P is equals to U plus AT. My initial final velocity at the very top is 0. My initial velocity in the question is 28.7. My acceleration is negative 9.81. I can calculate the time. 0 minus 28.7 will make it negative 28.7 is equals to minus 9.81 multiplied by time. So time is going to come out as, if I divide my negative 28.7 by my 9.81, I will get my answer as 2.92. Now, keep this in mind that this is the time for the ball or for the flare to travel from the starting position to the maximum height. Now,
So I have to times by
again,
2?
yes, exactly, because my
Okay.
launching position and landing position is almost the same. I'm launching from the water and it's landing in the water. Again, if it was landing on another surface, if it was landing on a cliff, then we would have to individually calculate the time for going up and for going down. In this question, I don't have to calculate individually for going up and going down because my uh, flare is going from the sea and landing back into the sea, right? So it's quite simple. I'll simply multiply it by 2. So if I multiply this by 2, I get my answer as total time for the journey comes out as 5.85 seconds. Now that I have the total time for the journey, I can simply go ahead and put it in my initial formula. Speed is equal to distance over time. So we want to know the horizontal distance. So I will use the horizontal speed. Horizontal speed is 49.7. I do not know what is the horizontal distance, but I do know that the total time taken is 5.85. So 49.7 multiplied by 5.85 gives me, just give me 1 second. It gives me a value of 290 meters. That means the horizontal distance covered by the flare is going to be 290 meters. They said the flare was visible from a maximum distance of 8 kilometers, right? So the horizontal distance we are getting is that we are getting a value of 290 meters, which if I want to turn it into kilometers, I will go ahead and divide it by 1,000, right? So divided by 1,000 to turn it into kilometers. So we get our answer of, so we go ahead and we get our answer of, so this is 8 kilometers, right? 8 kilometers means that it is 8,000 meters. So as you can see, maximum distance is 8 kilometers, meaning that if the flare has uh, um, if the flare um, if the flare is still up in the air, if the flare is still up in the air, or if the flare is traveling less distance, the maximum distance is 8 kilometers, meaning that if the flare is traveling more than 8 kilometers, it will not be seen. Why? Because it's traveling greater than 8 kilometers. The maximum distance from which it is visible is 8 kilometers. So if my flare is going past the 8 kilometers mark, it will not be observed. My flare is most definitely traveling less than 8 kilometers. It's actually traveling 290 meters. 8 kilometers is 8,000 meters. So we can conclude, yes, this flare is going to easily be seen by the rescue boat. Making sense how we're getting the answer and how we're solving the question?
Just a bit confused on the first line.
The last line about the
The
flare
first-
being visible.
About the maximum distance of 8 kilometers.
Right. So, okay, this is in the question. They're saying the flare was visible from a maximum distance of 8 kilometers. So, my flare is going to be traveling like this, right? So, when it's going to travel like this, it's going to cover a horizontal distance. Now, this is not my calculation. This is a data given by them. They're saying that the flare is visible from a maximum distance of 8 kilometers, meaning that the maximum horizontal distance that the flare can cover is 8 kilometers. As long as the flare is landing somewhere within the 8 kilometer, the rescue boat will be able to see it. That's what they're saying. As long as the flare is coming within the 8 kilometers, they're saying maximum distance from which it is visible is 8 kilometers. Meaning that when the flare goes up and it comes down, so that horizontal distance, the maximum distance we can have is 8. Right? We cannot have more than 8. If my flare travels greater than 8 kilometers, if it goes too far away, if it travels too much, the rescue boat will not be able to see it. So they were asking us, do you think the rescue boat will be able to see the flare? Do you think the rescue boat will be able to see the flare? So the maximum distance that the, when you're going to go ahead and talk about it, the maximum distance that your flare can be visible from is 8 kilometers. It cannot be visible past that 8 kilometer mark. Let's draw our boats. We have this is our launch boat. Okay. This is the distance traveled by the flare. Over here, I have my rescue boat. Okay. The rescue boat is 8.2 kilometers from the boat in distress. Right? So let's go ahead and take a look. Okay. Let's say now the rescue boat is 8.28 kilometers from the distress, right? We need to figure out if that rescue boat is going to be able to see that flare or not. They have given us a value. They have told us the value is 8 kilometers. If the flare is within that 8 kilometer mark, the rescue boat will be able to see it. That's the maximum distance. More than that, it cannot be, we cannot see it anymore, right? That's what we have to go ahead and we have to calculate. So let's say that the maximum distance is 8,000 meters. That's the radius they have given us. They have told us is this is the flare or this is my ship that is in trouble. So the maximum we can have is 8,000 meters or 8 kilometers or 8,000 meters in any direction. So let's make it a radius. That this is the ship in the middle and my flare can travel at, it has to maximum distance it can be visible from is 8,000 meters. Our boat is 8.2 kilometers or 8,200 meters away from the boat in distress. This is the rescue ship. Will this rescue ship be able to see our flare? So that is what we are finding out. So we know that the flare will travel a horizontal distance of 290 meters. they have said that the flare is visible from a maximum distance of 8 kilometers, right? So let's see. Our rescue boat is 8.2 kilometers and the maximum distance is 8 kilometers. If I subtract 8.2 from 8 kilometers, I get 0.2 kilometers. We need to see whether our boat will be able to overcome this difference of 0.2 kilometers or not. If this flare is able to travel far enough where it can overcome the distance between the rescue ship and that 8,000 kilometers, that 8,000 kilometers radius, if the distance between the two of these, the flare is able to travel far enough to overcome the small distance between the rescue ship and our radius, the rescue ship will be able to see it. If it cannot, it will simply fall somewhere over here and the rescue ship will not be able to see it anymore. So we are getting our value of 290 meters. 0.2 kilometers is equal to 200 meters. So that means our flare has to travel over 200 meters. If it travels less than 200 meters, then it will fall short. So our flare is traveling 290 meters, meaning that it will easily be able to cross that 8,000 meter radius, 8 kilometers radius, go up into the air and be observed by the rescue ship. So the flare will be observed. Now is it becoming a bit more clear? Now is it making sense? How we're drawing the final conclusion
Just confused me
based on our
because
values?
it says it's 8.2
Yeah, yeah.
kilometers and if it
Yeah,
would more than 8
yeah,
kilometers it will not be observed. So the closer
yeah.
it is, less like observable it is.
Okay, no, they're talking about the horizontal distance, that is flat distance. We are dealing with a projectile object that is going up in the air and then it is coming down, right? So that is exactly the scenario. That boat is 8.2 kilometers away. The flare is visible from a maximum distance of 8 kilometers, meaning, okay, what they actually mean by this statement is this. This is my boat. This is my flare. It goes up in the air, right? After it goes up in the air and let's say it lands, the boat, the rescue boat, has to be within 8 kilometers of this flare at any point, whether from the start or whether here or whether when it is landing. In the entire path of the this in the entire path of the boat, in the entire path of the your flare, the rescue boat has to be within 8 kilometers. You're thinking of 8 kilometers from the launch position. It's not just 8 kilometers from the launch position. Once that flare is in the air and I'm 8 kilometers away from it, I can see it. So it's not just from the launch position. It's from the entire pathway of the flare. From the entire pathway of the flare, the maximum distance that I have to can be away, the furthest away I can be from the flare is 8 kilometers. As long as I'm within the 8-kilometer marking of that flare, I will be able to see it. So that rescue boat was 8.2 kilometers away. So we had to determine 8.2 kilometers away. So at any point in its entire journey, could it have been observed by the boat? That's exactly what they were asking. In the entire point of the journey, it's 8.2 kilometers away. The maximum distance is 8 kilometers. So at any point at all, is that flare going to be within 8 kilometers of our boat? That's exactly what we had to discover. So we find out that the flare is traveling 2,290 meters. If I subtract 8.2 from 8, that's 0.8 kilometers, right? The boat is 0.2 kilometers away from the from, you can say, the radius, right? So when our flare in any point of its journey, is it overcoming that 200-meter difference between the 8 kilometers and 8.2 kilometers? So when our flare completes the entire journey, it's traveling greater than 200 meters, meaning that most definitely at some point in its journey, maybe around here, maybe because the total distance is 290, almost 300 meters, right? So maybe somewhere here, maybe somewhere here, at some point, the distance between our rescue ship and the flare is going to be within the 8 kilometers mark, and the rescue ship will be able to see it. So when they're saying maximum distance, they do not mean that the absolute maximum distance. They mean in the entire pathway. So from the launch position, yes, if I talk about from the launch position, they will not be able to see it because they're outside. They're away from the 8 kilometer mark. But when it goes into the air, when it launches up into the air, what happens? That when it goes up into the air, it has now traveled a distance of almost 300 meters, 290 meters. So that ship is 8.2 kilometers away. I have covered a distance of 290 meters. So let's subtract 8200 minus 290. I will get my answer if I go ahead and do that. I get my answer as 8200 minus 290. 7910. So this is 7.9 kilometer. So when the flare goes up in the air and it travels the entire distance, it is only 7.9 kilometers away from the rescue boat. The maximum is 8 kilometers. So the flare is 7.9 kilometers away from the rescue boat, so it will be observed. So it's not about from where we're launching it, because it's a projectile. It's about the entire travel. So when it is traveling, when it will land at its final position, it will be 7.9 kilometers away from the rescue boat because it has traveled a distance of 290 kilometers, right? It has traveled that 290 meters. So it has gotten closer to the rescue boat. So even though the rescue boat was originally out of the maximum distance, but because the projectile was able to overcome that gap, it was able to travel 290 meters. It was able to get close enough to the rescue ship. It was able to get within the 8 kilometer mark, and hence it was observed.
Yeah, I
I
understand.
hope that's making a bit more sense now.
Yeah, I understand.
Okay, all right. Okay, any more questions? I hope we're all good with the question, right?
Yeah.
All right, okay. Okay, guys, so we will go ahead and stop it over here for today. And then, inshallah, in the next class, we're going to go ahead and take a look at a few more questions on the topic. All right?
Just a good question. You know how in the question
Yeah.
it says there's an assumption that you've made.
Yeah. You want, okay, hold on. Let me just let me reshare that with you. This one, right? Where they're saying
Yeah.
state one assumption we have made over here in A3.
Yeah,
Yeah.
this one.
The assumption we have made is that there is no air resistance. That's the assumptions we have made. There is no air resistance. Because think of it this way, if I have air resistance, that means my acceleration is not constant. It's not going to be 9.81, right? Because my object is going upwards. Let's say I throw an object upwards, completely straight upwards, right? So what's going to happen, that we had studied this in IGCSE as well, as the object is going to travel upwards, what's going to happen? That we're going to have air resistance. That air resistance is going to decrease the acceleration. It's going to change the acceleration. It's not going to be 9.81 because now when the ball is going upwards, it has to deal with an upward force. Not only does it have to, so it's not just about the ball traveling upwards. It's not just about the ball going against the force of gravity or against the weight of the ball. Now there's air resistance. So the air resistance will further slow down the ball. So we are assuming that there is no air resistance. That's why we are taking our acceleration as 9.81. If you guys were doing this in actual practical in your lab or in your real life, you could not use 9.81 as it is because you guys would have to think about air resistance. But we always assume that air resistance is not there. Hence, we can use a constant value, fixed value of 9.81. So that's it. That was the basic assumption, and that's why it was just also a 1 mark question. The assumption is that we are not taking a resistance, or there is no a resistance in the question at all. Clear? Does that answer your question? All right.
Yeah.
Okay, guys. So we'll go ahead and stop it over here for today, and we'll continue on inshallah in the next class. All right.
When is the next class?
I'm sure they gave you your schedule. Give me